We're going to take an example of a circuit and perform an FMEDA on this circuit. This example is taken straight from ASIL 26262 chapter 5, and this is available in the annex. For today, we're going to take this example. And what this is a circuit that shows a microcontroller which consists of a couple of inputs, probably from some kind of a sensing element, and then there's a few outputs. There's a power supply, there's a watchdog over here, and it's all powered by a battery. There's a lot of simple components like resistors, capacitors. There's also more complex components like the microcontroller, which is an IC. The watchdog controller is also an IC, and it's a few transistors, and there's also an inductor over here. Now, the first step of performing an FMEDA is once we have all of these components, we have to create an FMEDA form sheet, which involves listing out all the components. So here is a screenshot of what that would look like. So this talks about R73, which is one of the resistive elements, and R73 here corresponds to this element over here. Similarly, you can see other components, 74, I71, which refers to different components. And notice that the first thing you'll already see is just transferring the elements from the architecture diagram or the circuit diagram into an FMEDA form sheet is already a lot of work. You've got to manually look at every element in the architecture diagram and transfer to the form sheet. Now, there's tools that help do this better, but this is topic for another video. So once we have a list of all components, then we need to estimate the failure rates for each of these components. Now, there's several ways in which failure rates can be estimated. The two most common ways. Number one is by using real life data. So if we have this resistor in production for the last 20, 30 years, and we know how many failures we've seen, then we can estimate. We have an idea of what the failure rate is. But many of the times we don't have this information because they're all new components, or we just don't have the information because the supplier of the resistor inductor is just not maintaining this. In this case, we'll have to use certain databases to estimate the failure rate. A couple of examples of these databases is IEC 62380. Alternatively, military handbook can be used if the applications are for military applications. There's an Storm database available. There's an FIDES database available. There's different databases available to estimate the failure rate. IC 62380 is very popular in the automotive, and that can be used to estimate the failure rate. Once we have the failure rate, or fit as they call it, for the component, for the component estimated, then we have to determine if a failure of the component can lead to a safety code violation. It may be that it's nothing to do with safety, so if the component fails, it might be okay. So in which case it would be a no, and if it's yes, it means that it is required for a safety standpoint. Then comes the failure mode distribution. The most common failure modes for resistors: open and close, open circuit and closed circuit. You could also have resistive drift. It's a very, very smaller failure mode, but depending on the type of the resistor, depending on the component, you'll have different set of failure modes, and they have different distributions. Now that we have component, its failure mode, and its distribution, we then need to analyze if a failure of this is it detected, can it be detected by a safety mechanism? Or even before that, we need to determine if a failure of this component in the absence of a safety mechanism can violate a safety goal. And if the answer is no, then we don't have to do anything about it. If the answer is yes, then we have to see what is the appropriate safety mechanism for it. So in this case, there is a safety mechanism which is called SM4. Now it will be it's a kind of a watchdog mechanism over here. And let's assume that it has a diagnostic coverage of 90%. What this now means is 90%. So of a failure mode of 100, this microcontroller has a failure mode of 100. This particular failure mode has a distribution of 50%, and 90% of this 50% can be detected by the safety mechanism SM4. But what that means is out of 100, the 100 fit, 50 fit is this failure mode. And out of 50 fit, 90% can be detected, and 5% cannot be, 10% cannot be detected. And 10% that cannot be detected is 10% of 50, which is 5. So what this means is 5 out of 100 will go undetected. The other 95 are either not safety relevant or can be detected. Now similarly, if there is a safety mechanism, we have to determine if there is a violation of a safety goal, if there is a fault of the safety mechanism itself. And in this case, SM4, a failure of SM4 can be detected. So it has 100% coverage with respect to latent faults, which leads to a latent point fit or latent point failure metric of 0. Now, at the end of all this, we have to find out the single point failure metric, which is, there's a formula for this. It's 1 minus residual fault by total safety related fault. And what the single point failure metric again signifies is if there is a failure, what percentage of the failure is safe. Safe either by design or safe either it is detected by a safety mechanism. Now, higher this metric, better it is. A 99% SPFM means 99 out of 100 failures are either not safety relevant or they're detected by a safety mechanism. And it's just the 1% that will go undetected. Now, similarly, a latent fault metric, that there is a formula for a latent fault metric. It is 1 minus the latent point failure rate divided by the total safety related failure minus the single point, the total single residual failure. Overall, the FMEDA, it is used to determine whether it's used to determine the single point failure metric and the length failure metric. And so from an ISO 26262 standpoint, for an ASIL B safety goal, 90% single point failure metric has to be achieved, which means over here we have a single point failure metric of 93.2%, which is more than 90%, which is good. If this happened to be an ASIL C safety goal, ISO 26262 recommends that 97% diagnostic coverage be achieved, and this is just not good enough, which means in order to increase this, you can see that the value of 9.65 has to be reduced, which would mean this value of 5 has to be reduced, or the other location where which is contributing to 4.65. That's just not shown here. And 5 can be reduced if this diagnostic coverage can be increased. So this could be made 99%. If it's 99%, then this would probably be 0.5, and this reduces, probably we can reach 97%. That is the whole idea behind calculating the SPFM alpha. We want to improve the diagnostics, or we want to improve the fit rates. So this is overall the idea behind the FMEDA. Overall, it is to see if the diagnostics has improved the system,